Good afternoon to all of you. We have completed two chapters. First chapter is introduction. Second chapter, the buffer cache. Now we are going to learn the third chapter, the internal representation of files. So syllabus of this chapter is introduction of internal representation of files. Then what is inode? Then regular file structure, then directories, then how to convert path name to inode, then what is a super block, then inode assignment to new file, then allocation of disk blocks and other file types. So for the whole syllabus, the recommended book is a design of Unix operating system by MJ Batch, and the course outcome will be, after learning this chapter, a student will be able to learn the structure of regular file, and by using these a student will be able to allocate a disk blocks. So what about the title? The title is internal representation of files. Every file, a Unix system has unique inode, that is index node. Processes interact with files using well-defined system calls. Different processes interact with a different system calls for their execution work. So users specify file with the character string, which is file's path, then systems get inode, then which is mapped to file which corresponds to the path. Then the central idea of the chapter. So this chapter describes the internal structure of files, which examines the inode and how the kernel manipulate it. Also examines the internal structure of regular files and how the kernel read and write their data. The structure of directory, the files that allow the kernel to organize the file system as a hierarchy of the files, and presents the algorithms for converting user file names to inodes. And finally, discussion about other file types, that is which are present in the system, that is pipes and device files. So the central idea of this chapter is the algorithm described in this chapter. We will study once again the algorithms we have studied in previous chapter, and that algorithms occupy layer above the buffer cache. So algorithm I get returns a previously identified inode, possibly reading it from the disk via buffer cache. The algorithm I put release the inode. The algorithm bmap sets the kernel parameters for accessing file. The algorithm name I converts the user level path. See the figure 1 carefully. See, this is the figure 1 for the introduction of a file system, allocation of different algorithms. See here, we have studied different algorithms in previous chapters such as get block algorithm we have studied, that is allocation of buffer or block to a particular process with five different scenarios. Then after work is done, then the buffer or block is reduced with B release algorithm. Then next we have studied buffer reader algorithm, that is B read algorithm. Then we have studied buffer read ahead algorithm, that is B read A algorithm. Then we have studied B write algorithm. So these algorithms allocated, that is buffer allocation algorithms, we have to study with these always as we have to study the name I algorithm. Name I part contains three parts of algorithm, that is IGET, IPUT and bitmap algorithm. Have any doubt? Then allocation of buffer and free of buffer. Similarly, allocation of inode and allocation of free, that inode, that is ifree, ialloc and ifree. This is the file system or different algorithms. So out of these five algorithms we have seen in previous chapter, get block, B release, B read ahead and B write. Now we are going to see the next seven algorithms such as IGET, IPUT, BMAP, alloc free and ialloc and ifree. So these algorithms as lower level file system algorithms, and in previous chapter we have seen the algorithms as buffer allocation algorithms. So what is the importance of this chapter in the subject? This chapter is important because it describes data structure and algorithms used internally by the file system. These algorithms take care of internal bookkeeping needed for managing user files. So, as seen in this figure, the inode contains, that is index node, which contains information necessary for a process to access a file, such as file ownership, file access rights, file size, file allocation, files data in the file system. Okay, we'll see one example. See, these are the different files. Suppose whenever I right click here, then go to the properties. Here, different parts in general, name of file, storage of that file, then that is the location, then size of that file, size on the disk, then when this file is created, at what day, date and time. Similarly, date of modified, day, date and time is modification. Then access, that is whenever it is accessed a date, day, time. In advanced, if we have seen, it have attributes as read only or hidden. Similarly, the advanced, that is file attributes, file is ready for archiving. Allow these files to contains index addition properties, or if you want to compress these attributes, so compress contains data, save data, disk place, or increase the contents of secure data. Similarly, whenever you should have taken any file, suppose here I have taken another example. So see here, same, whenever created, what time it is created, date, date, time. Similarly, modified date, date, time, and accessed date, date, time. Then what about security? Security, it has access permission, that is full control. Modify, read and execute a read permission, write permission, or other special permissions. Then details of these files, title, subject, different tags, then author of these file. Similarly, this is example you have seen Windows operating system. Similarly, these properties related to file in Unix operating system. So the inode contains the information necessary for the process to access file, such a file ownership, access rights, file size, location of files, data in the file system. Processes access files is a by a well-defined set of system calls, and specify file by a character string that its path name, and each path name is uniquely specify a file, and kernel converts path name to files inode. Each file, each path name is uniquely specifies file, and the kernel converts that path name to the files inode. That is, it gives a particular index number or index node to that file. So in this chapter, we are going to see the algorithms such as IGET, IPUT, BMAP, alloc free, ialloc, and ifree. So the algorithm IGET returns a previously identified inode. The algorithm IGET returns previously identified inode, possibly reading it from disk via buffer cache, and the algorithm input releases the inode. The algorithm bmap sets the kernel parameter for accessing a file. The algorithm name I converts a user level path name to inode using algorithm IGET, IPUT, and bmap. Using these three algorithms, the algorithm name I is the combination of three algorithms: IGET, IPUT, and bmap. Using these three algorithms, algorithm name I converts user level path name to inode. Similarly, the algorithms allocation and free allocates and free the disk blocks for files. Algorithms alloc and I free, that is assigns and free inodes for files. So in this section we are going to see what is inode, then accessing inodes and releasing inode. So what is inode? So inode, it exists a static form of disk. It exists a static form on disk, and kernel reads them into an in-core node inode to manipulate them. Inodes exist a static form of disk, and kernel reads them into an in-core inode to manipulate them. Disk inode consists of following fields. So file owner identifiers. There are three types of users. We have seen there are three types of users. We have seen in practical session. Read, write, execute, then read, write, execute, then read, write, execute. This group, this group is owner. This group, that is also known as user. This group is also known as user or owner. Then this group, that is group user, and this is other users. So a read R for a read, R for a read, W for a write, and X for execute. So read, write, and execute. These are the permissions for reading mode, writing mode, or executing mode. We have seen in this example. Suppose here we have opened a file. In properties, we see the, in case of security, here full control, that is modify, then read and execute, read, write, special permissions. Then so here, so for user read permission, for user side, a read permission, a value is a standard value is 400. A write permission, user value is 200. In case of execute, for execution, here 100. So it is 700. Similarly, in case of group user, read permission value is 40, write permission value is 20, and execute value is 10. Here value is 70. Similarly, for other users, So read is equal to value 7, write is equal to value read is equal to value 4, write is equal to value 2, and execute is equal to value 1. Total value is equal to 7. So combination of all these users value is equal to 777. Total value is 777. So user permission have 777. Suppose someone has given a value from 111 up to 777. So suppose I have written like code 5604. So this 5 indicates a permission for user, this 6 permission for group user, and these permissions for other users. So this 5 is a combination of read and execute. This 5 is combination of two values, read and execute. So it have permission read and execute only. There is no write permission. Instead of w we can write here dash. So read and execute only permissions. For 6, for 6 is a combination of write and read and write. So for here we can write read and write, no execute permission. And for other group there is a combination, only one, a read permission, there is no write permission, no execute permission. So in Unix operating system sometimes we see like these file permissions. So here starting, suppose a dash, then it is a file. Starting, suppose D, then it is directory. There are total 10 characters. See, count these numbers. There are from D to from this dash. There are total 10 characters. Okay. So inode exists a static form of disk. Inode exists a static form of disk, and the kernel reads them into in-core inode to manipulate them. Disk inode consists of following fields, that is file owner identifier, that is it is user or group user or other, then type of a file, that means files may be type of regular, a directory or character file or block file or FIFO, that is in case of pipes, first in first out. Then file access permissions, that is read, write and execute, these access permissions. Then file accessing time, that is creation of time, modification time and deletion time, that is accessing time, creation time, accessing time and modification time. So this gives a time the file was last modified, when it is last accessed and when it is last modified. These are the characters of file. Then the file has in directory hierarchy. There are number of links to the file. representing number of names. In hierarchy directory, we have seen that, or in first chapter, hierarchy of files, we have seen that a different file or a same name file at different location. So there are different links. So table of the contains disk address of data in a file. Although users treat data in a file as logical stream of bytes. Although users treat data in a file as a logical stream of bytes, the kernel saves data in discontinuous disk block. Whenever a table is created for disk addresses of data, then user treat data as logical user treats data in file as a logical stream of bytes, whereas kernel saves the data in discontinuous disk blocks. The inode identifies the disk blocks and contains the file's data. Then next point is file size. Data in file is addressable by number of bytes. The data in a file is addressable by number of bytes from the beginning of file starting from byte offset 0. The data in file addressable by number of bytes. Okay, and the file size is greater than the highest byte offset in the file. For example, if user creates a file and writes only one byte of data at byte offset 1000 in file, the size of file is 1001 bytes because it starts from 0. See, this is the example of inode of file. So suppose we have taken example of this file. Owner of that file is suppose mjb, whether group is operating system, the type of file is a regular, it have permission, that is read, write, execute, then read and execute, then read and execute. So there are three types of users: user, that is owner, others. Then this is accessed date time, this is modified date time, and this is inode created or changed date time. Then this is the size of that file and disk addresses. This is the example of inode. See the figure carefully. The next point is the in-core copy of the inode. It contains the following fields in addition to fields disk inode. The status of in-core inode indicating whether the inode is locked. A process is waiting for inode to become unlocked. The in-core representation of inode differs from the disk copy as a result of change to the data in inode. The in-core representation of the files differs from the disk copy as a result change in file data. The file is a mount pipe. So what is the status of in-core inode? Whether inode is locked, the process is waiting for inode becomes free. The in-core representation of inode which differs from the disk copy, which is different from the disk copy as a result of change the data in inode. The in-core representation of file differs from the disk copy as a result of the file in data, and file is mount point. Then logical device number of the file that contains the file. So logical device number of file, that's file system that contains the file which contains the inode number and pointers to other in-core nodes. The inode number, since inodes are stored in linear array, inodes are stored in linear array on disk, kernel identifies the number of disk inodes by position in the array. So whenever we identify a particular inode, or kernel identifies that particular number of disk inode by its position in the array, and the disk inode does not need this field. The other is pointer to other in-core inodes. The kernel links the inode on hash queue. Kernel links inodes on hash queue on a free list in the same way as the link buffers on buffer and hash queue, and buffer is free list. Buffer is on free list. Similarly, kernel links the inode on hash queue and its buffer free list. As we have seen in previous chapter, the buffer hash queue and buffer free list. Similarly, here inode hash queue and inode free list that points to the other in-core inodes, that is pointer to other in-core inodes, that is pointer to the other in-core inodes. So there is a reference count indicating number of instances of file that are active. How many times are the file is opened, number of times that are instances are active. Then many fields in the in-core include analogous to the fields in buffer header and the management of inode to the similar to the management of buffers. Many fields in the in-core inode are analogous or related to the fields of buffer headers, that is management of inodes similar to the management of buffer. In previous chapter here, allocation of buffer, we have seen there is get block algorithm. In that different five scenarios we have seen, that is for allocation of a buffer to a process. Similarly here, allocation of inode to a process. So here buffer header is analogous to the inode. The most striking difference between in-core inode and buffer header is the in-core reference count, which counts the number of active instances in the file. There is a difference between in-core inode and buffer header. So Buffer header shows the buffer number, whereas in core inode, which counts the number of times process or active instances of that particular file. So whenever the active inode is active, when process allocates it, such as when opening a file. Whenever the file is open, at that time inode is active and process allocates it. When inode is free on list, its reference count is 0. If the reference count of inode is 0, then it is free. That is, the kernel reallocate the in-core inode to other disk. Whenever buffer is free, buffer is allocated to that particular process. In previous chapter we have seen. Similarly, whenever inode is free, then kernel reallocates to a process and free list of inodes, thus services as cache of inactive inodes. If a process attempts to access a file, if a process attempts to access a file whose inode is not currently in core inode pool, the kernel reallocate it to the free list and for its use. On the other hand, buffer has no reference count. It is on free list if and only if it is unlocked. If buffer is not free, a buffer is free on list, it does not have a reference count, whereas inode is free on list, then it has a reference count. So we have seen the algorithm as a get block algorithm for allocation of block or buffer to a particular process. Similarly, here is algorithm for allocation of in-core inodes. We see here algorithm iget. Input is file system inode number, output is locked inode. So here, while not done, then it is true, then go to the next step in while loop. If inode is on inode cache, then again it check. If it is true, then check inode is locked. That is, whenever a kernel searches a particular inode, then that inode is on cache, then kernel checks whether it is busy or free. If it is busy particular inode, then the process go to the sleep mode up to inode becomes free. If inode is free on free list, so remove that from free list, increment inode reference count and return to inode. If inode number of nodes, sorry, if no inodes on free list, there is free list is empty, so remove new inode from free list. If no inode on free list, then remove new inode from free list, reset that particular inode number and file system, remove inode from old hash queue, place on new hash queue. See here same as a scenario 3. which we have seen buffer allocation or block allocation, that is in get block algorithm. Here, suppose kernel searches a particular inode number and which is not free, then kernel takes the free. Whenever kernel searches a particular inode number and which is not exist on that list or on that hash queue, then kernel takes a free inode from free list and allocates the particular number and place at proper place whenever it is required. So read inode from the disk as per buffer read algorithm. Then initialize inode reference count to 1 and return inode. This is the algorithm for allocation of icore inodes. So here we have used a buffer read algorithm, that is B read algorithm we have seen. So you should know the buffer reader B read algorithm for reading the contents of that particular buffer or reading the contents of inode. So you should know the B read algorithm. Then how to access inodes? So with a particular formula we can access inode. So this is the formula, that is block number is equal to inode number minus 1 divided by number of inodes per block plus start block of inode list. This is the formula for calculation of particular block number, that is inode number minus 1 divided by number of inodes per block. All these plus start block of inode list. For example, assuming that block 2 is the beginning of inode list and there are 8 inodes per block, then inode number 8 is in the disk block 2, the inode number 9 is in disk block 3. If there are total 16 inodes in a block, then inode number 8 and 9 are in block 2 and inode number 17 is the first inode of block 3. Suppose there are total 8 blocks, then block number 8 inodes, there are total 8 inodes, then inode number 8 will be reside into block number 2, because here we have taken block number 2 is beginning of inode list. So there are 8 inodes per block and there are total 8 inodes, then inode number 8 is in block 2. Suppose there are 16 inodes, then block block inode number 8 is on block number 2 and inode number 9 is in block number 3. Suppose there are 16 inodes in a disk block, then 8 and 9 are in block 2 up to 16. Then 17 inode number is the first inode of disk block 3. See here, suppose these are the disk blocks. This is disk block. Suppose Here we have taken from example disk block number 2, then disk block number 3, then disk block number 4, and so on. Suppose there are four inodes, four inodes in each disk block, four inodes in each disk block. Then here four inodes, that is first, this is a second, this is third, and this is fourth. Then fifth will be at block number 3. Then here 6, here 7th, here 8th, then ninth will be in here next block number. Similarly, there are suppose 8 inodes in each block. 8 inodes in each block. Then here 5, then 6, then 7, then 8 in the first. Then 9 will be the first inode of next block. If there are 8 in each block, then here 10, then 11, then 12, 13, 14, 15, and 16, and 17 will be the first inode of next block. If there are 16 inodes in each block, there are 16 inodes in each block. Suppose here block number 2, block number 3, block number 4, then block number 8 and 9 on inode number 8 and 9 are in block number 2, 1 up 2 up to 16, and 17 will be the first inode of next block. Okay, so when kernel allows device and disk block number, it reads block using the algorithm as buffer reader algorithm, that is B read algorithm. Then it uses following formula to compute byte offset to inode in this block, that is inode number minus 1 mod number of inodes per block. For example, here each disk inode occupies a 64 bytes and there are 8 inodes per disk. Then inode number 8 starts with the offset, that is 448 in the disk block. See here, the disk inode occupies a 64 bytes and there are total 8 inodes per disk block. So see here, there are suppose here this is block 1, this is block 1, and each block contains 8 inodes. This is first, second, third up to 8. Okay, this is 7. Then each inode contains 64 bytes Each inode contains 64 bytes. Then eighth inode. Here 64. This inode contains a 64 bytes data. Similarly, this inode contains 64 bytes data. This inode contains 65 bytes data. This inode contains 64 byte data. This inode contains 64 byte data. Then here starts from in first inode it starts from 1 to 64. Second inode starts from 65 to 128. Then third inode starts from 129 up to 192. Similarly, eighth byte starts on 448. Similarly, eighth byte, this is for first inode, this is for second inode, this is for third inode, and so on. For eighth inode, it starts from 448. So kernel removes the in-core inode from the free list, places on proper hash queue or correct hash queue, sets its in-core reference count to 1. So it copies the file type, owner fields, permission settings, link count, file size, and table contents from the disk inode to in-core inode. So we have seen the properties such as file type, file owner fields, permission, different permissions such as read, write, execute, then number of link counts, then files particular file size, and table of contents from the disk inode to in-core node, and returns a locked inode. So kernel manipulates the inode lock and reference count independently. Whenever kernel copy the all the contents regarding the file, all the properties regarding the file such as a type, field, permission, number of link count, size, what is the table contains. So kernel all manipulate inode lock and reference count independently. The reference count is remains a set across multiple system calls. The lock is free between system calls to allow permissions to share simultaneous access to the file. The reference count remains set between system calls to prevent the kernel from reallocating an active in-core inodes. So this is the algorithm as releasing an inode. Previous algorithm is IGET algorithm. Here algorithm is releasing an inode. That is first algorithm as we have seen allocation of inode. Here we can release the algorithm. So input for this algorithm is release access in core inode. Again input, that is this algorithm is also known as IPUT algorithm. Previous algorithm is IGET algorithm. So IGET algorithm, that is allocation of inode. IPUT algorithm for releasing that inode. So output is nothing. So here lock inode if not already locked. decrement inode reference count. And if reference count is equal to 0, then inode link count is equal to 0. And free disk blocks for files, set file type to 0 and free that inode. If file accessed or inode changed or file changed, update the disk inode, put the inode on free list and release the inode block. See the algorithm carefully. Previous algorithm we have seen as IGET algorithm. In that we can allocate the inode. So here algorithm is IPUT algorithm. Here we can release that inode. So what happens while releasing the inode? When kernel releases the inode, it determines its in-core reference count. If the count drops to 0, the kernel writes the inode to disk. If the in-core copy differ from the disk copy, they differ if the file data has changed, if file access time has changed, or file owner or access permission have changed. The difference between in-core copy and a disk copy due to file access permission, file owner or access time, whatever the parameters have given has been, there is a only one difference, they are differ from each other. The kernel places the inode free on list, effectively caching the inode in case it needed again soon. The kernel may also release all data blocks associated with file and free inode if the number of links to the file is 0. Then what is the structure of a regular file? The inode contains tables of contents to locate files data on disk. Since each block on a disk is addressable by number, the inode contains a table of contents to the locate files data on disk. Since each block on a disk is addressable by a number, the table of contents consists of set of disk block numbers. If the data in a file were stored in contiguous memory location or contiguous sections of the disk, then storing start block address and the file size in the inode would suffice to the access of data in the file. Such allocation strategy would not allow for simple expansion or contraction of file system without running risk of fragment, free storage or disk. See in this example, see this is a memory allocation of suppose 8 byte or 8 bit 1 byte memory allocation to here continuous memory allocation. Suppose this is first, a second byte, a third byte, fourth byte, fifth, sixth, and seventh byte memory. And suppose there are five file or three files: file A, file B, file C. This is suppose 8 byte. This is suppose 10 byte, and this is suppose a 12 byte. So file A stored here total 8 byte 0 to 7. Then file B or sorry here 1 to 8 we can calculate here 1 to 8. So first 8 bits goes to the file A. Then for contiguous memory allocation, file B requires 10 bytes, but here 8, then here 16, then here 24, then here 32. So this is 8 byte memory allocation. This is 8 byte memory allocation. So it allocates first 8 bytes to B, then remaining 2 bytes here, that is here 18. 2 bytes allocated in, it is in continuous memory allocation. Then then C requires 12 bytes here, 6 bytes are remaining, 6 bytes. So here B6 and 6 bytes memory is allocated here, and next 6 bytes memory is allocated here, then C6, that is here 30. This is in continuous memory allocation, but sometimes in non-continuous memory allocation, see here, then 1, then 8, then 16, then 32, sorry, 24, then 32, then 40. So see here, your first location, your first, second, then third, then fourth, fifth, sixth, and so on. So first location file A is allocated as 8 byte, but here B requires 10 bytes. So out of them, first 8 bits allocated here, B 8. So then here file C, here file C, first 8 bit is allocated here. So C8, then remaining here 2 bytes, that is B9 and B10. So here allocates B9, 10, whatever data, and here 26, then remaining 6, that is C 9 up to 12, up to 30. This is non-contiguous memory location, and this happens in inode. Okay, so inode contains a table. Inode contains the table of contents to locate files disk. Since each block has a disk addressable by number, table contents consist of set of disk block numbers. If data in file were stored in contiguous memory location, then storing start block address, file size in inode would suffice the access data in the file. However, such allocation strategy would not allow for simple expansion and contraction of files in the file system without running risk of fragments free storage area of the disk. This is the structure of a regular file. See here, file A, file B, and file C. This is a continuous allocation of files. See here, of file A, uh, file A is requires 10 unit data. File B requires 11 unit data. File C requires again 10 unit data. This happens in continuous memory location A after B after C. But in non-continuous memory allocation, file A same, then there is a free, then file free, because this contains a 10 bytes 10 unit data, whereas B requires 11 unit. So this memory block remains free, then allocates file C, then it takes next 11 11 unit of memory for file B. This is the allocation, non-continuous allocation. Here continuous allocation, whereas a figure below second figure, this is non-continuous allocation. But there is a fragmentation of free space. So what is the structure of a regular file? See in from previous figure, there are three files A, B, C consisting 10 disk blocks storage, and suppose the system is allocated storage for three different files continuously. If the user wants to add 5 blocks of data in the middle of file B, the kernel will copy the contents to file B and place in the file system for 15 blocks of storage. So aside from expense of such operation, the disk block previously occupied by B is unusable. Here suppose there are three different files ABC and each occupies 10 units of memory locations. There are three different files ABC and each occupies a 10 different memory locations. Suppose file A, this is file B, this is file C. So each file contains a 10 memory units of locations. So this is in continuous, but whenever the user wants to add, B contains a 10 units, whereas A also contains a 10 units, C contains a 10 units, but user wants to add 5 units data in that file, so size of file becomes 15 units. And for locating the file system B in this file system, it is not useful. So here, see here, A is stored as it is 40. A is stored because A is 10 units. After A, there is B, but B requires 5 units extra, so it becomes free. Then C allocates next 10 units. Then, whenever the extra memory space is remaining, then allocates B, that is here 85, and so on. So the kernel would have copied the contents of file and place in file system. It is hard. So aside from expenses, such operation, the disk block previously occupied by B's data would be unusable except the files for smaller than 10 blocks. Suppose, see here, this is happens in case of increasing the files. Suppose user has reduced, suppose file contains, see here, A is 10, C is also 10, but B also 10, but instead of it has reduced size, suppose by 2 units, then it becomes 8 units. So how it is allocated? Suppose here file A 40, then 50, then file B 60, then C 70, whatever. So whether it is exactly equal to 10 units or less than 10 units, it is usable space. But more than 10 units, it is not usable, or that space is not useful for that particular file. Whenever the size of that file is increased, the particular assigned space is unusable except a smaller file, smaller than particular assigned blocks. So kernel could minimize the fragmentation of storage space by periodically running garbage collection procedures to compact available storage. So for greater flexibility, kernel allocates file space one block at a time, allows data in a file to be spread throughout the file system. But this allocation scheme completes the task of location data. The table contains could consist a list of block numbers. Such block numbers contains table contains could consist a list of block numbers such that block number contains data belonging to the file, but simple calculation show that the linear list of file blocks in inode is difficult to manage. So if logical block contains 1 KB, if logical block contains 1 KB, then file consisting of 10 KB would requires index of 10 block numbers. If memory unit assigned as 1 KB and the file contains data up to 10 KB, then such memory requires 10 times or 10 different block 10 block numbers, but file containing the 100 KB would require 100 block numbers. So either size of inode vary according to size of file, or relatively low limit would have to be placed the size of file. Whenever file size is increased, you should have to increase the inode, or relatively low limit would have to be placed the size of the file. So to keep the structure small yet still allow large files. So how to decrease that files? So keep that structure of file small, so that large files are allowed. Table contents of disk block confirm that, as shown in the following figure. See that figure carefully. This is the direct and indirect blocks of inode. See the figure carefully. See in this file, this in this example, the file size and inode size the file size is less than this inode size, so we can directly access. So direct 0, direct 1 up to direct 9. If file size is increased, suppose, see here, s- suppose this is 10 units of memory locations. Each memory location contains 10 units. Here, suppose 40, 50, then 60, 70, and then 80, and so on. So, suppose there are four files A, B, C, D. So, A contains less than A contains less than or equal to 10 units memory location. So A resides as it is, no problem. It is directly accessed whether the size of file and inode is less than or equal to than inode, then it is directly accessed. If this file, suppose file B is contains two 19, it requires suppose 19 units, 10 to 19, it requires 10 to 19 units data. Then there is nearly about single access, because here, see in this figure, there is a single indirect. We can reduce that file size by giving a link. With the reference link, we can reduce that file size so that we can access. This is a single indirect. We can direct access when the file size is less than or equal to the given inode block. If the file size is increased, so it can file size is reduced with the given indirect access or given a particular link to that file, so we can reduce. So there are a double indirect or triple indirect in the same way as single indirect. So the system 5 Unix runs with 13 entries in the inode table contents, but the principals are independent of the number of entries. In previous figure, we have seen total 13 entries, 0 to 9, 10 entries, 0 to 9, 10 entries, which are directory entries. Then next three entries as a single indirect, double indirect, and triple indirect. So these 13 entries inode table of contents, but principals are independent of number of entries. So blocks marked as a direct in the figure contains number of disk block contain the real data, and the block marked as single indirect refers block that contains list of direct block numbers. To access data via indirect block, kernel must read indirect block to find appropriate direct block entry. So the For accessing data via indirect block, kernel must read indirect block. Here from 0 to 9, this direct there is a direct block or direct access. But for indirect block, kernel must read the indirect block to find appropriate block entry, then read the direct block to find the data. The block marked double indirect contains list of indirect block numbers, and block marked triple indirect contains it is a list of double indirect block numbers. So kernel access inode and converts the logical file block into appropriate disk block. So the figure gives algorithm bmap for converting the file. Follow the algorithm. There is algorithm that is bmap algorithm, that is block map of logical file bytes offset to file system block. Bmap algorithm as it is a block map of logical file byte offset to the file system block. So input is inode and byte offset. Output is block number in the file system, byte offset to the block. Then third output will be bytes of input output in block. Fourth output read ahead block number. Then next calculate logical block number in file from the byte offset. In previous slides, we have seen the formula for calculating particular block number in a file from the byte offset. So calculate sort by block for, so it is a second output you will get, that is input output number. Then calculate number of bytes copied to user. This is third output. Then check if read ahead applicable. If it is applicable, then you will get fourth output. Then determine level of indirection. So while it is not necessary level of indirection, then execute this while loop and calculate index into the inode or indirect block form logical block number in file. Then get disk block number from inode or indirect block. Then release buffer from previous disk read by using algorithm release. Then if no more levels of indirection, then return block number. Read disk, that is algorithm bread. By using algorithm bread, read that indirect disk block. Then adjust logical number in a file according to the level of indirection. And this is the algorithm for block map of logical file byte offset into the file system block. See the algorithm carefully. So this is a figure of sample file and its inode. So this is a table index. Here one example we have taken, which is a direct access data block from inode. That is, suppose I want to access file number 367, which is direct access the data block 367. Here indirect access for data block 4 times 3. So first goes to the index number 9156. Here index number goes to that index number which is double indirect, and in that stored or given a link, that is 331. For single indirect goes to that 331. So here 331 is stored at 0th level address in double indirect. So goes to the 331 single indirect. So at 75 address number, so the link is stored as 4 times 3, and read that data of 4 times 3. So this is sample layout of file and its inode. See the figure carefully. So we are going to see structure of regular file. Assume that the disk block contains 1024 bytes. If process want to access byte offset 9000, the kernel calculates the byte in direct block 8 in the file counting from 0. Then it access the block number 367. Then we are going to study directories. So directories are the files that gives the file system its a hierarchical structure. They play a vital role or important role in the conversion of file name to an inode number. Directory is a file whose data is sequence of entries. Directory is a file whose data is a sequence of entries, each consisting of inode number and name of file contained in the directory. A path name is a null terminated character string, that is a slash character, and each component except the last must be the name of the directory. Hmm. Name of the directory, but last component may be the non-directory file. Each component except last must be the name of directory, but last component may not be non-directory file, but last component may be a non-directory file. So there are so many components from first to last in the directory hierarchy. So the sequence or name of directory except other than last is a directory part, but last component may be a non-directory file. The system 5 restricts the component's names to maximum 14 characters with 2-byte entry for each inode number, and the size of directory is a 16 byte. Maximum 14 characters with 2-byte entry for the inode number, and the size of directory entry is 16 bytes. See, this is the simple file system tree or hierarchy of file tree. The slash indicates a root directory, whereas first system one, binary, etc., user, Unix, device, these are the directories. So, directory layout, this is the standard for etc. of directory system. This is the standard directories, standard inode numbers and byte codes they have given. Then this figure shows the layout of etc. directory. Every directory consists name with dot and double dot. Every directory must consist of here dot and a double dot. Directory consists with dot and double dot whose inode numbers are those directory and its parent directory respectively. Every directory contains the file names dot and dot dot whose directory numbers of this directory and its parent directory respectively. The inode number dot is associated with offset 0. See in this table here 0 and its inode number is 83. The inode number of dot of etc. directory is associated with offset 0 in the file and its value is 83. The inode number of double dot is offset is 16 and its value is 2. Offset is here 16 and its value is a 2. So directory entries may be empty indicated by inode number of 0. Directory entries may be empty indicated by inode number 0. For example, entry address at 224 is empty. See here, entry address here in offset, entry address at 224 is 0. 224 is 0 and that file or directory is a crash directory is 0. So program mkfs initialize the file system dot and dot dot of the root directory have the root inode number of the file system. So this is the first figure. We have seen the different algorithms of this internal representation of file system. In this there are total 12 algorithms. So out of these 12 algorithms, 5 algorithms for buffer allocation algorithm, 5 algorithms for buffer allocations we have seen in previous chapter. Now we have seen the three algorithms such as inode allocation, that is igate, inode release such as iput, and bmap, that is block map. So there are four algorithms are remaining: alloc, free, ialloc, and ifree. So how to convert a path name to an inode? We are going to study conversion of path name to an inode. So here the initial access to a file is by its path name as in the open change directory, that is a chdir, or link system calls, because kernel works internally with inodes rather than with path names. So there is a need to convert path name to an inode. Kernel works with inode rather than path name. It converts path names to inodes to access files. And for conversion of path name to inode, here algorithm is name I, which parses the path name one component at a time. Converting the each component to an inode is based on its name and the directory being searched, and eventually returns inode of the input path name. So here we are going to see algorithm for conversion of path name to an inode. So algorithm name is name I. The input for this algorithm is path name. Then output is locked inode. So check the path name starts from root. If the path name starts from root, then working inode is a root inode. And by using algorithm igate, allocate to that inode, or allocate that path to the inode, or root to the inode if starts from the root. Otherwise working inode is current, so directory inode, and allocate a directory inode, allocate a directory inode by using igate algorithm. While there is a more path name, while there is a more path name, read next path name component from input. Read the next path name component input. Verify that working inode is of directory. Verify that working inode is of directory. Access permission. If it is accessible, then it is okay. If working inode of is root, then component is dot dot. If working node of root, then its component is dot dot. And then continue. Read directory working inode. Repeated these use of bmap algorithm, b read algorithm, and b release algorithm. Use these algorithms. If component matches an entry, if component matches an entry in directory, get inode number for matched component, release working inode algorithm input, release working inode with I put algorithm, then working inode, if inode match the component, then allocate inode with iget algorithm, otherwise return with no inode and return with working inode. Okay, see the algorithm carefully with different cases. In this algorithm we have used 5 algorithms. First I get, second I put, third B release, B read, and BMAP algorithm. See this algorithm carefully. For converging path name to an inode, this algorithm is known as name I algorithm. Don't write roll numbers. Don't write roll numbers. In this algorithm, name I uses intermediate inodes. It parses a path name, call them working inodes. Inode where search start is the first working inode. The name I algorithm uses intermediate inodes and it parses the path name, calls on working inode, then inode where search starts is first working inode. During each iteration, the name of during each iteration of name I loop, kernel makes sure that working inode is indeed that of directory. Otherwise, system would violate the association of non-directory files. The process must also have permission to search the directory. Only read permission is insufficient. It requires other permissions also. So user ID of the process must match the owner or group user ID or other, and execute permissions must be granted. The file must allow search all users, otherwise search fails. The kernel does not the kernel does a linear search of directory file associated with working inode, trying to match the path name component to to a directory entry name. We will see in next lecture a super block consists of what is a super block and its properties whatever in next lecture. Mm, Before going